Hey everyone, welcome back to my YouTube channel Let's Code for Fun, and welcome to my playlist The Wrong Way. And today we are going to see some uh, good ways to implement how to find if a number is prime or not. So yes, let's get started. So our problem statement is, you can see it over here. Okay, let me just remove this. So our problem statement is that we are given this function and we have to implement this. So we will be passing an integer n, and we will need to return whether the number is prime or not. Okay, so that's for refreshing. A number is prime if it has exactly two divisors, uh, one and the number itself. So yes, let's get started. So one of the simple brute force way what we can do is, let's say we can start with I equal to 1, I less than equal to n, I plus plus. If n is divisible by n, then div plus plus, and then if div is greater than or equal to 2, return false, else return true, greater than 2. So we can see that okay, let's define int div equal to 0. So div is basically the count of the divisors. So if the number of count of divisors is greater than 2, then we will return false, else would return true. So there are some scope of improvement here. What we can do is, we can start the loop from 2 itself, and we will say that the first time we see a number, we can start the loop from 2 and end it before n, and we can say that if let's say if any number between 1 and 2 divides, like if any number between 2 and n minus 1 and n minus 1 divides this number n, then we can say that it's a prime number, right? So we can say like n percentage I equals 0, then we'll return false, okay, else we'll return true. Now let's write some edge cases. Some edge cases would be that if n less than equal to 1, then return false. Okay, so yeah, so this would be a bit better than the last version, but it will still be O of n in the worst case. Like imagine that this n itself is a very large prime number, so none of these numbers between 0 to n minus 1 would divide it, right? So this loop would run for the whole uh, like almost n times, so the whole time complexity would still be O of n in the worst case. There are some cases in which we will be optimizing, but in worst case it is still O of n. Okay, so how can we optimize this? So before that, let's learn one simple theoretical concept. So we will try to prove that there will be, if the number is a non-prime, there we can find at least one number before its a square root which will divide it. Okay, so let's see an example. So let's say we have this number 24, and let's try to write all the divisors of 24. So we have 1, we have 2, we have 3, we have 4, we have 6, we have 8, we have 12, and then we have 24. So these numbers are all divisors of 24, right? So as you can see, all the divisors of any number, they exist in pairs. I'll tell you what I mean. So 1 and 24, because 1 times 24 is 24, right? Then again 2 and 12 equals 24. Again with the same with 3 and 8 equals 3. Okay, 3 and 8 equals 24, and similarly 4 and 6 So you can see that 3 into 8 is 24, 4 into 6 is also 24. So all of these numbers, if you see that the divisors of 24, they all exist in pair, and this is not only true for 24, this is true for all the numbers. So one thing you can notice is that at least one of them will be less than uh, square root of n. Okay, because let's say if can we say that both these numbers are greater than square root of n? It can't be, right? Because let's say if x is the divisor of let's say number n, so x divides n, and then y then n divided by x equal to y, that is also a divisor of n, right? So as we can see here, if 3 divides 24, so 3 divided by 8, what is 3 divided 24 divided by 3 is 8, that is also a divisor of 24. So if x divides n, n by x equal to y is also a divisor of n. So we can say that x into y equal to n, and we can say that if not both of them can be greater than square root of n, because if let's say if x is greater than square root of n and y is also greater than square root of n, then we will have something like square root of n greater than square root of n times greater than square root of n. So two numbers greater than square root of n, which means that the whole number is greater than n, which is a contradiction, right? Because we proved here that x into y is equal to n. So at least one of them would be less than equal to square root of n. So we don't need to run our loop from 1 to n or 2 to n. We can just run from 1 let's say 2 to square root of n. So yeah, let's see it in action. SQRT n and if n percentage. Okay, so now if you see that the time complexity of the whole function is O of square root of n. Now do you think that this is correct? This is almost correct, but still we have something that we should take care of. This square root function might not work if this integer n is long. So instead of sqrt, you should write sqrtl, right? Again, one thing, if you can notice that this is also a fine method, but then this sqrt gets sqrtl gets calculated each and every time the loop is run. So instead what you can do is let me just write this here: for int I equal to 2, I into I less than equal to n, I plus plus. So you can see that this is nothing but the same thing as sqrt ln, right? Both of, do you think that this is correct? So think about it. I mean, you can pause the video and think about it for a moment and then comment. So this is almost correct, also almost correct, because if you notice that this I into I can also overflow. So let's say if this this is a very long number, this is a very large number, then I into I will be, let's say I is 10 to the power 5, and to 10 to the power 5 into 10 to the power 5, and since it's an integer, the whole, this is overflow, and integer overflow is actually undefined in C++ standard. So you will not get the number which you want. So instead what we can do is see, I'm telling you all this because this is something which I have experienced. People do this mistake a lot of times, and a lot of times they're not able to find where it is. So instead of int, always try to make it long. You should always try to err on the side of caution. So yes, so I hope this was helpful to you guys, and I hope you learned how we and I hope you guys are liking this series, how we start from doing things which are very less effective, and then we are moving towards doing things which are more effective and correct. So yeah, goodbye, take care. I'll upload this video. Thank you.